Okay, so let's continue with Tasklets today. Um, I think we have some time to do some programming, like implementing some Tasklets. So I actually ended up just creating a new branch of the Linux 2.6.34 code base, simply because I think I want to try something different today where I actually create new header and C files to see how we would add new files to the kernel if we were to actually submit a kernel patch if we were in the year 2010 or whatever this version was out. Or like, let's say you're writing a driver and you need to submit the driver to kernel. So it's gonna be a good exercise, I think. More or less the same thing, just figure out how to trigger a bottom half interrupt handler. Well, hard to say. Try to trigger a bottom half handler for a specific interrupt, and have it run at a later time. So remember, we trigger these bottom halves, or we raise them, or schedule them, whatever you want to call it, right? We do that at the top half. So any of those critical handlers, then we raise them. And we've already learned that one way to do that is through soft IRQs. Second way to do that is now what we're going to be going over is Tasklets. Yeah. So yeah, just wanted to let everyone know I'm just creating off a new branch. So anyway, so I went through. Let's start over again. Might as well. Okay. So Tasklets. Okay. Tasklets are a bottom half mechanism built on top of soft IRQs. As mentioned, they have nothing to do with tasks. Tasklets are similar in nature and behavior to soft IRQs. However, they have a simpler interface and relaxed locking rules. As a device driver author, the decision whether to use soft IRQs versus Tasklets is simple. You almost always want to use Tasklets. So remember that soft IRQs are kind of reserved for very, very special situations. Most of the time, when we want to create bottom half handlers, we use Tasklets. So as we saw in the previous section, you can almost count on one hand the users of soft IRQs. Soft IRQs are required only for high frequency and highly threaded uses. Tasklets, on the other hand, see much greater use. Tasklets works just fine for the vast majority of cases and are very easy to use. Okay, implementing Tasklets. Because Tasklets are implemented on top of soft IRQs, they are soft IRQs. As discussed, Tasklets are represented by two soft IRQs, high soft IRQ and Tasklet soft IRQ. The only difference in these types is that the high soft IRQ based Tasklets run prior to the Tasklet soft IRQ based tasks. So remember we saw like in interrupt.h. Let's just go there. I think we saw that there was like a high soft IRQ, right, in this enum. So this is like the first soft IRQ that gets run in order. And so we can probably treat this as like a high priority tasklet versus this is like a normal priority tasklet right here. So the tasklet structure. Tasklets are represented by the tasklet structure. Each structure represents a unique tasklet. The structure is declared in linux/interrupt.h. So here's a tasklet struct. Basically, it looks like it's a linked list with a next pointer, and it looks like it's one of those recursive linked lists, not the kernel linked list style that we were used to seeing. It has a state. Oh yeah, I remember this. And then there's like an atomic number count. Then we have the handler here. This is what we're going to use to invoke code. And then here's the argument that we pass into this function here. So the func member is the tasklet handler. It's equivalent of action to a soft IRQ and receives data as its sole argument. The state member in the struct is exactly 0, tasklet state sketch, or tasklet state run. Tasklet state sketch denotes a tasklet that is scheduled to run, and tasklet state run denotes a tasklet that is running. As an optimization, tasklet state run is used only on multiprocessor machines because a uniprocessor machine always knows whether the tasklet is running. It is either the currently executing code or not. The count field is used as a reference count for the tasklet. If it is non-zero, the tasklet is disabled and cannot run. If it is 0, the tasklet is enabled and can run if marked pending. Scheduling tasklets. Scheduled tasklets, the equivalent of raised soft IRQs, are stored in 2 per processor structures. Tasklet vec for regular tasklets. So basically tasklet vec will probably be storing everything that is related to the tasklet soft IRQ. And then we also have tasklet high vec, maybe for these guys here, high soft IRQ tasklets. Both of these structures are linked lists of tasklet structures. So going back here, we notice that there was a linked list here. Okay. Let's see what else. Each tasklet structure in the list represents a different tasklet, so they're all linked with each other, and whenever you raise one, I guess, or register one, it's just one after another. So tasklets are scheduled via the tasklet schedule, so that's how we raise a tasklet or schedule one, and tasklet high schedule functions, which receive a pointer to the tasklet struct as their lone argument. So these things take a pointer to a tasklet struct. Each function ensures that the provided tasklet is not yet scheduled, and then calls __ tasklet schedule and __ dunder, right, tasklet high schedule as appropriate. The 2 functions are similar. The difference is that one uses tasklet soft IRQ and the other one uses high soft IRQ. Writing and using tasklets is covered in the next section. Now, let's look at the steps tasklet schedule undertakes. Okay. Okay, so this is what happens when you schedule a tasklet. Okay, so we check whether the tasklet state is tasklet state sketch. If it is, the tasklet is already scheduled to run and the function can immediately return. So that means at this point, some other processor is already taking up the tasklet. So that's how it knows not to do that. I think in this case, every CPU core has their own version of that queue. So then if they see that in memory that this one is scheduled, it'll skip that. Otherwise, tasklet schedule dunder is used, the inner function. So saves the state of the interrupt system, then disables local interrupts. When we say disable local interrupts, it means interrupts on the core CPU. This ensures that nothing on this processor, when we say this processor, we can think of that as core, will mess with the tasklet code while tasklet schedule is manipulating tasklets. So now we add the tasklet to be scheduled to the head of the tasklet vec or tasklet high vec linked list, which is unique to each processor in the system. Raise the tasklet soft IRQ or high soft IRQ high soft IRQs. So do soft IRQ executes this tasklet in the future. So that's like an important thing to consider, is that internally, if you think about it, when we call tasklet schedule, that calls dunder tasklet schedule. And we can just kind of think of it like this. Internally, that eventually calls raise. Was it called raise soft IRQ? Or is it, yeah, raise soft IRQ here. Okay, so it calls raise soft IRQ. Oops. And that takes in the argument of Tasklet soft IRQ or high soft IRQ. So it's all being abstracted away. Okay. Okay. Now, so then next, once we raise it, we're out of the function, or we're going to get out of function. So restore interrupts to the previous state and return. Okay. So at the next earliest convenience, do soft IRQ is run as discussed in the previous section. Because most tasklets and soft IRQs are marked pending in interrupt handlers, do soft IRQ most likely runs when the last interrupt returns. So, okay. So do soft IRQ is only going to run when every other interrupt is done. Okay, because Tasklet soft IRQ or high soft IRQ is now raised. Do soft IRQ executes the associated handlers. These handlers, Tasklet action and Tasklet high action, are the heart of the Tasklet processing. So Tasklet action, I think this is one of these. Yeah. As a function that will run them, I think. So let's look at the steps these handlers perform. So we're going to look at these steps, what happens in these functions. So these functions will now disable local interrupt delivery. There's no need to first save their state because the code here is always called as a soft IRQ handler and interrupts are always enabled. So that's the implication there. And then we will retrieve the appropriate Tasklet vec or Tasklet high vec list for this current processor, so the current CPU core. Okay. Now we'll clear the list for this processor by setting it equal to null. So, not sure what really that means. Let's see. Enable local interrupt delivery. Okay. Again, there's no need to restore them to their previous state because this function knows that they were always originally enabled. But why did we do that in the first place? I'm still not. Oh, yeah, because of the. Okay. All right. Okay. Loop over each pending tasklet in a retrieved list. Okay, and this retrieved list is going to be this Tasklet vec or Tasklet high vec. Okay, so that's each element in that list. So if this is a multi-processing machine, check whether the Tasklet is running on another processor by checking the Tasklet state run flag. That's important because we can't execute two of the same Tasklets at the same time. That's the simplicity guarantee of using Tasklets, is that we don't have to worry and stress too much about the kernel synchronization aspect of it. If it is currently running, do not execute now and skip to the next pending Tasklet. Recall that only one Tasklet of a given time may run concurrently. Yeah. Okay. So now, if the Tasklet is not currently running, set the Tasklet state run flag so another processor will not run it. Okay, so remember we went from Tasklet state schedule now to Tasklet state run. So check for a 0 count value, count member in that Tasklet struct to ensure that the Tasklet is not disabled. If the Tasklet is disabled, skip it and go to the next pending Tasklet. So I think if it's a if the count is non-zero, then that means something is actually working on it. So we now know that the Tasklet is not running elsewhere. Mark it running so that it will not start running elsewhere and has a zero count value. Return the task or run the task handler. After the Tasklet runs, clear the Tasklet state run flag in the Tasklet state field. Repeat for the next pending Tasklet until there are no more scheduled Tasklets waiting to run. So the implementation of Tasklets is simple but rather clever. As you saw, all Tasklets are multiplexed on top of two soft IRQs. So they're essentially just sub soft IRQs of these two soft IRQs, high soft IRQ and tacit soft IRQ. When a tasklet is scheduled, the kernel raises one of these soft IRQs. These soft IRQs in turn are handled by special functions that then run any scheduled tasklets. The special functions ensure that only one tasklet of a given type runs at the same time, but other tasklets can run simultaneously. All this complexity is then hidden behind a clean and simple interface. Sure. So here we go. This is how we would use them or create our own tasklets. Using tasklets. In most cases, tasklets are the preferred mechanism with which to implement your bottom half for a normal hardware device. Tasklets are dynamically created, easy to use, and quick. Moreover, although their name is mind-numbingly confusing, it grows on you. It is cute. Okay. Declaring your tasklet. You can create tasklets statically or dynamically. What option you choose depends on whether you have or want a direct or indirect reference to the tasklet. If you are going to statically create the tasklet and thus have a direct reference to it, use one of the two macros in Linux interrupt.h. So we can either use declare tasklet with these three arguments going in, and that's a macro, or we could use declare tasklet disable, which also takes in those three same arguments. So both of these macros statically meaning that we create the tasklets in the kernel code. It will be compiled, not loaded dynamically or created dynamically from other code. So it's inside the kernel code. Both of these macros statically create a struct tasklet struct with the given name. When the tasklet is scheduled, the given function func is executed and passes the argument data. Okay. The difference between the two macros is the initial reference count. The first macro creates a tasklet with a count of 0, and thus the tasklet is enabled. So this disable or declare tasklet will run the tasklet not disabled. Okay, so it'll run right away. The second macro, which is going to be the tasklet disabled version, sets the count to 1 and the tasklet is disabled. Here's an example. So given this macro here, we use these three arguments into this macro. It expands to struct tasklet struct my tasklet with null 0, and then the state or the count here is atomic. So initialize atomically to 0, and then we'll have the handler, and then we'll have the argument that gets passed into the handler called dev. And this is an unsigned long, I think, from what we saw up there. Unsigned long, unsigned long, unsigned long. Yeah, unsigned long data right there. Okay. Okay, so this creates a so this creates a tasklet named myTasklet enabled with the tasklet handler as its handler. The value of dev is passed to the handler when it's executed. To initialize a tasklet, given an indirect reference, a pointer, to a dynamically created struct tasklet struct t. So t is the dynamically created struct tasklet struct Remember, this is if we wanted to I guess create our tasklet dynamically, not statically. We use this tasklet init thing here. That's going to initialize t, which is at this point empty tasklet struct, give it the tasklet handler, and then also the dev. So this is dynamic way to do it. This is the static way to do it. We're going to probably try to do it statically today. So anyway, so writing your tasklet handler. So the tasklet handler must match the correct prototype. So we just need this type of function here. As with soft IRQs, tasklets cannot sleep. This means you cannot use semaphores or other blocking functions in a tasklet. Tasklets also run with all interrupts enabled, so you must take precautions. For example, disable interrupts and obtain a lock if your tasklet shares data with an interrupt handler. So implementation wise, Tasklets responsible for any locking necessary if you're going to be accessing shared data. So no guarantees from the kernel, up to you. Unlike soft IRQs, however, two of the same tasklets never run concurrently. But again, that doesn't mean anything, because if you're accessing shared data, you still need locking mechanisms. Because you could be accessing like data that is going to be accessed by other tasklets, not necessarily the tasklet of the same type in this case. So although two different tasklets can run at the same time on two different processors, if your tasklet shares data with another tasklet or soft IRQ, you need to use proper locking. Then we'll talk about that in the next chapter, chapter 9, an introduction to kernel synchronization, and chapter 10, kernel synchronization methods. Okay, so now once we have all that declared and registered, how do we actually like invoke a tasklet? How do we do stuff, right? How do we make it run? So this is what scheduling tasklet means. To schedule a tasklet for execution, tasklet schedule is called and pass a pointer to the relevant tasklet struct. So tasklet schedule is what we use, and then we pass the pointer here, see how we have ampersand, to our tasklet struct. After a tasklet is scheduled, it runs once at some time in the near future. So we would call this in some sort of top half handler. So I'm going to go back and leverage the I8042 interrupt handler because it's easy, So yeah, that's what we'll be doing. We'll probably be raising it there, similar to how we did it with the soft IRQ raising. If it is already running, for example, on another processor, the tasklet is rescheduled and runs again. Okay, as an optimization, a tasklet always runs on the processor that scheduled it, making better use of the processor's cache. You hope. You can disable a tasklet via a call to tasklet disable, which disables the given tasklet. If the tasklet is currently running, the function will not return until it finishes executing. Alternatively, you can use tasklet disable no sync, which disables a given tasklet but does not wait for the tasklet to complete prior to returning. This is usually not safe because you cannot assume that the tasklet is still not running. Okay. And then a call to tasklet enable enables a tasklet. This function also must be called before a tasklet created with declare tasklet disabled is usable. For example, tasklet disable my tasklet. So you now disable the tasklet, then you do all your stuff, and then you enable it again with the pointer to your tasklet struct. Okay, so you can remove a tasklet from the pending queue via tasklet kill. This function receives a pointer as a lone argument to the tasklet struct. Removing a scheduled tasklet from the queue is useful when dealing with a tasklet that often reschedules itself. This function first waits for the tasklet to finish executing and then removes the tasklet from the queue. Nothing stops other code from rescheduling the tasklet, of course. This function must not be used from interrupt context because it sleeps. Okay, so we have enough information to start creating our own tasklet. So with that being said, let's just start planning it out. So I want to do something different this time. I want to create this tasklet code in a different file and then just schedule it from I8042 interrupt handler. So I'm just gonna say like maybe have like a goal here, right? A goal. Make it more obvious as a G. Okay, schedule Tasklet to run from the I8042 keyboard interrupt. Okay, interrupt, and that is going to be in, I think it was like I8042 interrupt function. Okay, so that's the goal. So how do we get there? So first, I would say create two files. Okay. First, we want average dev.h and average dev.c. Okay. Now, average dev.h is just going to contain I think it was a declaration of the tasklet struct. Oops, the tasklet. Of the tasklet. Okay. And then average dev dot c is going to contain contain the handler information or implementation. Struct. Okay, and then implementation. So average dev h, average dev c is going to contain handler implementation for the tasklet, and also statically create one. So statically create using declare. I think it was called declare tasklet, right? Let's see. Oops. Declare tasklet. So this my tasklet thing is going to be from average dev.h. Handlers can be average dev c, and then we can just pass in whatever there. Okay, so go back. Declare tasklet. Okay. Next, modify I8042. I think it's called just I8042.c maybe in interrupt handler. And include, wait, yeah, hold on, in the interrupt handler to call tasklet schedule with the tasklet declared from or in, I think in, right? Yeah, in average dev.h. Okay, so we'll modify that, and that means we need to include it too. Include two. So we need to go back to our top half interrupt handler to just call tasklet schedule, getting that tasklet that we actually declared in average dev.h, the pointer to it, And then yeah, and then that would already have memory and stuff allocated because we did the whole declare tasklet in average dev.c. Next, modify make files to include average dev.h and average dev.c. Okay, and then where does average dev goes? I think it's going to include Linux. That's where all the header files should be placed at, and this should be placed maybe same directory as i8042.c, wherever that is. It sounds like a plan. Okay, so let's first create our average dev.h and include Linux, and then we'll find where i8042 is directory wise, and then we'll create average dev.c. That'll be like a first step. Okay, so here. So if we were to go to let's say, oh, we are in here. So let's do this. Let's create average dev.h in include Linux. So we're already in include Linux because we're looking at interrupt.h. So I think it's just like this %h to get to the same directory, and then we can call it average dev.h. Yeah, so include Linux average dev.h. And then we could just do like a if and def underscore Linux average dev h, define Linux average dev h, and if, and then we can say declare the Tasklet struct here. Okay. Next, let's find the i8042. I think this one, serial i842.c, and then we can just say we can look for the i8042 interrupt function right there. Maybe there. So it's right here is where we're going to again tasklet schedule whatever here. So I want to create basically the average dev.c in this directory here. So I'm going to just say was it e%:h average dev.c, and there we go. So I'm just going to include in this case Linux average dev.h just cuz, and then should be okay. Save that. Okay, now so I've created those two files, and now I want to declare. So the average dev.h is going to contain the declaration of the Tasklet struct, and how that looks like is going to be, so we want my Tasklet, so that looks something like something like this. So we just need to do maybe extern structs, Tasklet structs, average dev Tasklet, or something like that. So if I were to go back to, let's see, here, I think I can just do something like extern my, or extern struct Tasklet struct, something like that, average dev Tasklet, extern being that it should, do we need extern? I don't know. I've seen it before. Hold on. What's a good place? I know. Let's just look at Tasklet schedule and look for something that that has a similar declaration. Let's see, Tasklet struct. Okay, we have a lot here. Might not be that, huh? Let's see. Actually, there's something like keyboard dot C. Huh, here. Where were we at? Ooh. Drivers char. Maybe we did that tasklet. Okay, keyboard tasklet. Let's look for keyboard tasklet. Okay, so we want to find a declaration for this keyboard tasklet. So if I were to go here and do keyboard tasklet, should find that declaration. How did they do that? Let's see. Extern struct, tasklet struct, keyboard tasklet in kbd kern.h. Okay, so that's the right approach. I should probably yank that too and include it in my average dev h. So this one, yeah, maybe. Do I even need that? Let's see. Okay. So, and I probably need it on what? I'm including it there. So then on my .c, I don't need it. So now, if I were to go to average dev.c, so I've already included average dev.h. Going to here, I'm going to make a handler for the tasklet and then also statically declare the tasklet. So, first things first, how do we actually do that? How do we declare that function? Let's see. What is the handler name? This one, void tasklet handler unsigned long data. Okay, so we can, since this is going to be private function, we can static void average dev tasklet handler. We could say, what was it, unsigned long? Yeah, unsigned long data. Unsigned long data. Okay. Then we'll do stuff here. You know what? Let's just print k, kern info. And we'll say, oops, no comma, average dev. I am here. New line. Okay. And then we'll declare tasklet. We already have our average dev tasklet, so we could just import that here. And then the tasklet handler will be average dev, what is it? Tasklet handler. And then our dev would be, I don't know, let's see, how do we declare it? What are we passing again? Func data. Okay, so let's just pass in some integer. Let's just do 1. Actually, let's do 1, 2, 3. Okay, so now we've declared the tasklet. Missing defaults int. So should we just say something like unsigned long, like that? No. Zero? Let's just do 0. Whatever. Let's just do 0. Let's just see what happens. So, and then let's just do something very complicated. Let's do I fell for this once before. Int I, declare that. For int I, oops, I equals 0. I is less than, I don't know, 20 again. Let's do cubed this time. I plus plus. We can say, okay, print k, current info, average dev. The value of I to the 3 is, and then do that. And then we do I times I times I, just to make it do something. And then, okay, so we have all that. And then now we need to schedule that. Yeah, so we scheduled that with the pointer to average dev tasklet. So if we go here to I8042, here should be a good place. So we can use Tasklet schedule with the pointer to average dev Tasklet. Now we need to include then Linux/average dev up here. Something like that. Okay. Okay. Yeah, like all these reds, I don't know. It just keeps doing that. So I'm just gonna ignore it. And then so yeah, so remember, like, Tasklets are just the same thing as like soft IRQs in that they achieve the same bottom half purpose, so it makes sense to just schedule it in some sort of top half in this case. So it should run the same way as a soft IRQ, but Tasklet style. Yeah, so let's do this. Let's add makefile. So let's see here. Where are we at? Input serial makefile. Okay, so we have I8042.0. We want to just, how do we do this? Let's just add it with it. What's it? Average dev.o. Okay, so that's how we're gonna add it. This just like adds it if, you know, I think this evaluates either you statically compile it versus compile it as module. So if I8042 is enabled for kernel config, it'll just now compile with not only I042.c but also a average dev.c to get the object file. I'm not sure we need to do anything for headers though. Let's see. So do we? Let's see. Is there anything in here? No, there's not. So I'm gonna trust it. Okay, so maybe we can compile it now. So we go here. So basically what we're doing now is we're just doing the same thing as yesterday, where we raise some bottom half handler, like schedule it. In this case, we're using Tasklets now, and we follow the directions of how to create a Tasklet. First, I did it by just creating new files to see how we actually add new files to Linux kernel. So I just declared the Tasklet struct this way, and then I implemented it, or at least a handler privately here, to just do something silly. And then I just did declare Tasklet down here with the average Tasklet, which I got by including this one here. Also included the handler. So let's see. We should, I guess, also do this. Data is going to be LD data, just so. Okay. Yeah, let's just compile it. It's a good exercise to kind of learn how to add new things to kernel, I guess. So cd average dev, cd linux, make j24. So let's see. If it starts compiling without any errors, I'm going to pause and then come back when it's done. But it looks like it's already almost done. Looks like it's a incremental compile. So we might be good on that. Yeah, it looks like we're almost done already. All right, I'm just gonna pause it. Okay, so that looked like it's done. Again, sudo make install. Then sudo reboot and see what happens. Oh, it looks like it is working. Interesting. I just saw them logging. So that works for sure already. Okay. All right. Just for good measure, let's type something. And then the message. There you go. I am here, data. So that we just achieved the same thing, but now with Tasklets as Soft IRQs. So every time we type, we basically have one of these things here. So we just did that. Okay, so at 55, I guess, I just did it again. So let's see how many times we executed it. So yeah, completely useless, but we have something. So um, let's finish this up with K Soft IRQ. Yeah, let's do that because we're going to transition to work queues next. Okay. So, K Soft IRQD. Soft IRQ and thus tasklet processing is aided by a set of per processor kernel threads. These kernel threads help in the processing of soft IRQs when the system is overwhelmed with soft IRQs. Because tasklets are implemented using soft IRQs, the following discussion applies equally to soft IRQs and tasklets. For brevity, we will refer mainly to soft IRQs. Because tasklets are soft IRQs essentially. So as already described, the kernel processes soft IRQs in a number of places. Most commonly on return from handling an interrupt, soft IRQs must be raised or might be raised at high rates, such as during heavy network traffic. Further, soft IRQ functions can reactivate themselves. That is, while running, a soft IRQ can raise itself so that it runs again. For example, the networking subsystem soft IRQ raises itself. The possibility of a high frequency of soft IRQs in conjunction with their capability to remark themselves active can result in user space programs being starved of processor time. Okay, that would be bad. Not processing the reactivated soft IRQs in a timely manner, however, is also unacceptable. Okay, so now you're like in this weird situation. When soft IRQs were first designed, this caused a dilemma that needed fixing, and neither obvious solution was a good one. First, let's look at each of the two obvious solutions. The first solution is to simply keep processing soft IRQs as they come in and to recheck and reprocess any pending soft IRQs before returning. This ensures that the kernel processes soft IRQs in a timely manner, and most important, that any reactivated soft IRQs are also immediately processed. The problem lies in high load environments in which many soft IRQs occur that continually reactivate themselves. Ooh. So, the kernel might continually service soft IRQs without accomplishing much else. User space is neglected, so it's kind of like denial of service. Indeed, nothing but soft IRQs and interrupt handlers run, and in turn, the system's users get mad. This approach might work fine if the system is never under intense load. If the system experiences moderate interrupt levels, the solution is not acceptable. User space cannot be starved for significant periods. That's how important user space is. The second solution is to not handle the reactivated soft IRQs. On return from an interrupt, the kernel merely looks at all pending soft IRQs and executes them as normal. If any soft IRQs reactivate themselves, however, they will not run until the next time the kernel handles pending soft IRQs, which is basically the next time the interrupt occurs, or the next time a new interrupt occurs. So they're just going to sit there in the queue. This is most likely not until the next interrupt occurs, which can equate to a lengthy amount of time before any new or reactivated soft IRQs are executed. Whereas on an otherwise idle system, it is beneficial to process the soft IRQs right away. Unfortunately, this approach is oblivious to which processes are runnable. Therefore, although this method prevents starving user space, it does not starve the soft IRQs and does not take a good advantage of an idle system. Okay, so that's, I mean, it works when the system is busy, but when the system is idle, this approach to running the soft IRQ that was activated on the next interrupt doesn't really work in that sense. So, in designing soft IRQs, the kernel developers realized that some sort of compromise was needed. The solution ultimately implemented in the kernel is to not immediately process reactivated soft IRQs. Instead, if the number of soft IRQs grows excessive, the kernel wakes up a family of kernel threads to handle the load. The kernel threads run with the lowest possible priority with a nice value of 19, which ensures that they do not run in lieu of anything important. This concession prevents heavy soft IRQ activity from completely starving user space of processor time. Conversely, it also ensures that excess soft IRQs do run eventually. Finally, this solution has the added property that on an idle system, the soft IRQs are handled rather quickly because the kernel threads will schedule immediately. There is one thread per processor. The threads are each named kSoftIRQDN, where n is the processor number. On a two-processor system, you would have kSoftIRQD0 and kSoftIRQD1. Having a thread on each processor ensures an idle processor, if available, can always service soft IRQs. After the threads are initialized, they run in a type loop like this. So basically, they just constantly check if there's a soft IRQ, they schedule, and then they run the soft IRQ until there's no more pending. So if we look at that, just going back to here, actually let's pick one here. Oh, that's my flame shark. Let's do it here. This has been running for so long. All right. So let's do btop. Okay, so we have btop. So I have a 12 thread CPU. So therefore, if I were to do soft IRQ, it's already filtered. I have 12 of these kSoft IRQ threads running. Okay, so yeah, so they do that job of handling all the soft IRQs. I'm not sure if this thing here shows priority. Let's see, info, status sleeping, so it's not really doing anything right now. Anyway, yeah, okay. So if any soft IRQs are pending as reported by soft IRQ pending, kSoftIRQD calls do soft IRQ to handle them. Note that it does this repeatedly to handle any reactivated soft IRQs too. After each iteration, schedule is called if needed to enable more important processes to run. After all processing is complete, the kernel thread sets itself task interruptible and invokes the schedule to select a new runnable process. The soft IRQ kernel threads are awakened whenever do soft IRQ detects an executed kernel thread reactivating itself. All right, I think that's enough for today.